right, so halohydrins, these guys here, halohydrins, were initially made reference to in chapter 9 when we worked on epoxide chemistry, because we learned that we can just treat a halohydrin with a strong base such as sodium hydride. Remember, this is sodium plus, H minus, so H minus could deprotonate this OH, making it into a nucleophile, then would do an intramolecular displacement, intramolecular substitution of this bromide to make the epoxide. This chapter, when we're dealing with alkene chemistry, we can figure out how we are going to synthesize halohydrins. We need to put bromine on there, at least in this halohydrin, it's a bromine. It could be a chlorine or an iodine. So we have to assume bromine, probably going to have Br2. And then what's going to have the OH? It's going to be water. So these are the conditions to form a halohydrin from an alkene. And there are going to be components of this that look like a lot of the reactions that you've seen previously, the mechanism. The first part of this reaction, we are still in the same type of reactivity, right? We're doing an addition reaction. We have our pi bond where the electrons are. That negative is going to flow to a positive or to a weak bond. And we said that the X2 bonds are weak. Br bond, II bond, those are weak bonds. So the pi bond is going to add to those to break that weak bond. And that adds to the other side to make those halonium ions, and in this case, it's a bromonium ion. And at this point, we have to think back to a variety of concepts, right? When we have just Br2, Br minus is the only thing that's around, right? And Br minus is able to open up that three-membered ring. But we don't have just Br minus around. We also have water around. So the question becomes, which of these is a stronger nucleophile / base? Acting like a nucleophile here, so which is the stronger nucleophile? So how do we relate nucleophilic strength? We think about the strength of the base and relate that to the conjugate acid. So the conjugate acid of these would be HBr and H3O+. As far as pKa's go, this is negative 1.7, and HCl is negative 7. HCl equals negative 7. So how does HBr relate to HCl? Br is even more stable as the ion, so HBr would have a pK even lower than negative 7. So what does that tell us? What's a stronger base / nucleophile? The stronger acid has the weaker base, stronger acid, weaker base. So this is the stronger base, the stronger nucleophile. So instead of Br minus adding to the bromonium ion, the water is going to act as a nucleophile to do that instead. So that would make we would add to one side, open it up, and it would be anti-addition. So let's make this dashed. So the Br is now dashed. The OH2 is now positively charged. It's a oxonium ion, and then water. There's lots of that around. That will do the final deprotonation to make our halohydrin. So that's how halohydrin's made. This is a separate reaction, right? So it's not like these things are around at the same time that sodium hydride's around. This reaction happens first. We purify that, and then we do the epoxide forming reaction. So that's a halohydrin. Course packet says halohydrin formation is an example of blank addition. Is it syn addition or is it anti-addition? Well, the groups are opposite directions. They're not the same direction, that is anti-addition. So that's what you would put in that blank. All right, so we've seen the general mechanism of halohydrin formation, but we are yet to see something where there could be different products formed depending on how, what atom the oxygen versus the bromine or halogen added to. So that's what regioselectivity is. What is the relationship between these two? They would be constitutional isomers, same molecular formula, different atomic connectivity. So constitutional isomers, another name for them is regioisomers. What's the difference? Well, the OH is where the bromine is, the bromine is where the OH is. So you guys have the tools to work through this mechanism and decide which one the product is, and it really relates closely to epoxide chemistry. So be thinking about that when you try to work through this. So you pause the video, you did that, you worked through it. You got to our intermediate where we have the bromonium ion. And what can we compare that to? Well, we have epoxides that we've looked at before, and essentially what we said was that when we had an epoxide that was protonated, it weakened one of the bonds. Which of the bonds did it weaken? So I'm trying to draw the similarity between these two. This is not existing right now, but it's a similar situation. So one thing we looked at with the epoxide situation was the length of these various bonds. And we have the same thing computationally created here for the bromonium ion. What we see is that the bond lengths are very different for the different positions. So 2 angstroms here and 2.4 angstroms there. So pretty substantial differences there. So what's going on? So this kind of doesn't look like that. What it looks like more in reality is this. And why is that? Well, we have a formal positive charge on the bromine. That's kind of a bookkeeping tool. But the bromine doesn't really want to be positively charged. It's pulling electron density away from the carbons that it's attached to. And the one that is best at holding that charge is the more substituted one. So it's putting a very substantial partial positive there, a much smaller partial positive at the less substituted position, because this is almost like a tertiary carbocation, right? So it would be a more stable position for that partial positive. And what we saw with the epoxides, and we're seeing it again here, is the bond to the more substituted position is longer. Remember, it was about 2.4 angstroms versus 2.0 angstroms, which if it's a longer bond, it's also usually almost always a weaker bond. And the nucleophile wants to pick off the bond that is weakest. We want to break the thing that is weakest. That's what going downhill means. So the nucleophile adds to the position to break the weakest bond. Weakest bond. And that was the same situation with these epoxides. When we had a protonated oxygen of that epoxide, when it was positively charged, it weakened this bond, and the nucleophile added to that position. If the epoxide was neutral, it was a different story, but when it was a positively charged epoxide, that's how it works. And again, we're trying to draw our similarities here. Positive epoxide, positive bromonium ion, the regioselectivity is the same. So the water molecule is then going to add to that more substituted position. That would give us OH2 plus and Br there. Water would then deprotonate that to provide this as our product, and this would not form right there. Again, hopefully you're not seeing this as like, oh, another reaction that I have to remember. Hopefully you're thinking through the mechanism, understanding the mechanism, and relating it back to mechanisms that you formerly understood. Because all of the organic reactions we learn generally follow very similar trends. So if you're focusing on the mechanisms, that's what's going to help you.